Okay, well, I think we're a couple of minutes after the advertised starting time, so I think we should make a start now. So welcome everybody to this second in a series of coffee talks, which are brought to you by the Global Forum for Geography and Statistics, GFGS, in partnership with the United Nations Economic Commission for Europe and the European Free Trade Association, EFTA. So this time we have a slight change of topic, but there will be some links, as you'll see later on in the presentations. Here we're looking at something called the DGGS, Discrete Global Grid System. And those of you working in statistics or in geospatial information will be familiar with many, many acronyms. This one's a fairly new one for me, maybe for some of you as well. So we have an introduction first from Robert Gibb from Landcare Research in New Zealand. And then we'll go on to look in more detail at some applications with Matthew Pearce from Pangaea Innovations in Australia. And I would also like to just mention that our two presenters are joining us in more or less the middle of their night time. So particular thank you to you for doing that. Okay, so I hand over then to you, Robert.
Thank you very much, Stephen. And it's a privilege to be talking to you all at whatever time of day or night you happen to be joining us. Okay, so quick introduction to myself. So in fact, both Matt and I have been leading the standards process for discrete global grid systems in OGC, the Open Geospatial Consortium, and also in ISO TC 211. So that's a quick background. Myself, I've been a researcher with Manaki Whenua Landcare Research for just about my whole career, and they are laboratory in the environmental space. So that's, and I've been a modeler with them. So that's my reason for coming across discrete global grid systems as a solution to the modeling problems that I encountered in my spatial analytical career. Okay, so our talk is in two parts, as Stephen implied. So I shall do the first part, and then Matt will do the second part. So I'm going to start off by looking at what are reference systems, because the discrete global grid standard starts off by defining a discrete global grid reference system. And it's a little bit different from traditional reference systems. So a reference system is simply a system for identifying position in the real world. And traditional spatial or temporal reference systems provide answers to either where is something or other, or when is it. And there have been two types developed in ISO TC 211 and OGC. One is referencing by coordinates, and they are covered by those two standards in the spatial sense and the temporal sense. And the other is by identifier. And once again, there are two different standards there for identifier-based referencing systems. And just to give some examples, coordinates, pretty familiar with them. So I've got latitude, longitude there. And then the second one is an eastings and northings on a sheet that happens to be called 13S. And on the time space, I've got a date there, or a Julian day number. There's two examples of coordinates in the spatial domain. And then names like London or New Zealand or Yorkshire, or even C08204, a postcode, those are all valid geographic identifiers. And in the temporal systems, the identifier variant is most often used for ordinal eras, in geological time. So Cenozoic, Jurassic, and so forth. And these reference systems reflect our thinking over, it's evolved over many centuries. But I suppose the question we need to ask ourselves is, are they fit for purpose for the demands of spatial data in today's world with the use of computers? Now, those reference systems have, so let's have a little look at the data and what we need to do to the data to use it in these systems. Those of you familiar with vector spatial analytics and geographic information systems will know that there are things like, we talk about points and lines and polygons. And we also have more recently things like point clouds from LiDAR, even tag clouds from social media. And all of these things are ways of representing geometry in a structured file format. And there are many, many different structural formats for files, and every vendor tends to come up with their own additional suite. And height and time may be added as coordinates, or they may be added as attributes, or even put in the metadata. A timestamp may be put on a whole data set and put into the metadata. And then topology, which is things like, what's the spatial relationship between these two features, is then computed from the feature geometry. And that's the way we do it in the vector space. Slightly different with rasters, but once again, rasters are used, for observation type uses. And once again, there are many different image data formats, and they all have their pros and cons. And we have an open source library, GDAL, which assists us with reading all of these and with doing the conversions between them. And this plethora of formats has also brought about quite a variety of programming interfaces as well. And we can tile them, and if we do, that's an entirely implementation specific things. Once again, there are standards for how you do tiles. And once again, time may be in the metadata, or it may be in an additional band name, for instance, in Earth observation data. We can also have map data that's represented as raster data as well, and the same thing we have here. We have often have zoom levels defined, and those can be different resolutions. But overall, we get this theme coming through that the coordinate reference system is completely independent of the dataset format and the API. So the coordinate reference system doesn't provide any geometry or topology. If we're dealing with names, then we have gazetteers, disambiguate identifiers, different uses of them. And we also have topological hierarchies, things like counties are unions, or countries, should I say, are unions of states, counties or regions, and they might contain cities and suburbs, and streets and houses might be in suburbs. And this knowledge is represented as RDF facts, or is often represented as RDF facts. And so this is the topology associated with identifiers. And we have a language, Geospatial, which provides the spatial language and reasoning capability on top of the spatial use here. And identifiers, when we look at the standard, the identifier insists that each identifier has an interior position. And we can also see that you can have topological facts, and there may or may not be formal boundaries of these entities. So the geometry is optional. But what's interesting here is that you can use any database at all, or XML or JSON to store lists of identifiers and RDF facts. And the spatial and temporal specialization becomes a language issue rather than a data format issue. So we've got a distinction between the two different approaches to the reference systems we have. But that distinction means that, in fact, one is good for one set of things and the other is good for other different things. You know, if you need geometric precision, then you're unlikely to be working in an identifier space. So what if we had a reference system that natively provided identifiers, position, geometry, and topology? Can we retain the simplicity of referencing by identifiers and make position and topology explicit and precise, and add geometric robustness of referencing by coordinates? And if you like, that is the challenge that we've been addressing with discrete global grid systems. And the latest version of the specification, which is OGC Abstract Specification Topic 21, version 2, and also ISO 19170, part 1. These are both submitted for publication, so they've been through all of their voting processes in January, and in due course, sometime over the next month to a year, these will appear as actual published standards. And they specify this new form of referencing, and we call it referencing by zonal identifiers with structured geometry. So the focus is on the identifier, but we have structured geometry. And this is the reference system used by discrete global grid systems. Well, that's all very well, but what might this look like? And so here we have an example of a globe, and this is using a discrete global grid system that I happen to have had a hand in creating. And what we've done here is we've pretended that the globe is a cube. So we've got 6 faces, which we label N, O, P, Q, R, S. And then each of those faces we treat as if it's a rectangle, and we tessellated it 3 by 3 into 9. And each of those faces, then we recursively continue to tessellate it. And each time we add another tessellation, we add another digit to our identifier. And so we have something like this. And this particular length of identifier gives you about a ½ kilometer pixel. And we have topology because we can have, you know, the children associated with this. And we can do the topology of the neighbors. So this one here has its neighbors, and it has neighbors of multiple sorts. And so fundamentally, this is the sort of approach we use. And so what does this mean for data? Whereas before we had coordinates, now we have things represented by pixels. And I think this illustration shows both square pixels and triangular pixels and hexagonal pixels. And that's because you can have DGGSs of any of those flavors. And a critical thing here is that each of these data types is now being represented by simply a list of identifiers, the identifiers associated with each of those pixels, or each of those zones as we call them. And we have 2 bonuses here. One is that in the new version, the ID can represent both time and space. So we can go from 2D through to 3D, through to 2D plus time, or 3D plus time. And the language we use and the fact that it's in a single identifier doesn't change. And there's a second bonus as well. And that is the zone size that we choose to use is representative of the spatiotemporal precision with which that knowledge is known. And that's a very important thing to be able to add in. And we do the same thing with raster data. And once again, we just have lists. And once again, the zone size is represented for data precision or of your needs for tiling performance. And so we now have this list of spatial types. We have an ordinate list, a cell list, a tile list, a directed ordinate list, a directed cell list. These are equivalent to lines. A directed tile list, that might be an ordered job queue, for instance, or a zone collection or a directed zone collection, which is a collection of in a mixture of these other types here. So you can see that it's highly repetitive, and fundamentally, pretty simple. So traditional reference systems, no, there's no such thing as reference system data, but with DGGS there is. And now we have, as we said with identifiers, the spatial properties or spatiotemporal properties are now a function of the language. So what does that language look like? Well, it turns out we already have a topological language, and it thinks it's, you'll recognize all of these things: buffer, difference, intersection, equals, overlaps, all of those sorts of things, and we can do all of those. We also have a new set which we add to that to navigate that hierarchy in the pixels. So we have child, parent, and sibling, and the tests child of, parent of, sibling. And we also have a pair of new 1D operators borrowed from time, and these can query any dimension. So this is relative position and relate position. And so when it's referred to time, it's things like before and after. But any axis that has a direction to it can have a before and after. So you can have you could have that as being north of or south of, or east of or west of, or above or below. And so those operators can relate in those directions as well. And all of the operators with stars can also control the level of detail that you want the result sets. So that's pretty powerful as well. And also you can have a lower dimensionality query of a higher dimensional DGGS. So if you've got a 4D DGGS time, you can still issue a 2D query, or you can ask for the query to be executed in 2D. And so this is what they all look like. And as you can see, there's a highly repetitive pattern to them. But as you can also see, and that is that the geometry would traditionally have been given by sequences of coordinates or something rather like this, whereas now it is just the zonal identifier. And so that's the key thing that I want you to sort of capture from this. So how can we apply this? Over to Matt.
Okay. Good afternoon, everyone. I won't go too much into into my bio, but as Robert said earlier, both Robert and I are sort of one of a core sort of group of people who've been leading the development of discrete global grid system standards for the last sort of 4 or 5 years, we're on to version 2 of the main standard, but we're also now extending into the open API space to provide consistent leverage. So without going too much more down that path, we'll talk a little bit about the application of DGGS to statistical use cases. So if you just advance again, there we go. So as Robert sort of showed the sort of an overview of DGGS, this is I guess a similar thing. I call it sort of the DGGS on a page. So one of the things about DGGS, particularly equal area DGGS, is that they're all fundamentally based on a polyhedron that's mapped to the surface of the Earth, that implicitly gives us the equal areaness, which then can be refined down to sort of microns or even smaller, or up to global, which gives you an immense range of scales that you can operate in without having to change your infrastructure. Just advance one more, please. There we go. And as you'll see at the top there are different polyhedrons, and they lead to different sort of types of tessellations. And so fundamentally, we end up with there are sort of two fundamental DGGS shapes, and then if you sort of augment the triangular one, so you've got squares and triangles, you can then construct hexagons, which from a closeness, a close packing perspective, and a sort of an aerial coverage perspective, is a really good option from a uniform coverage perspective. A little bit more complicated than the square one, but it's the main point here is that there are different styles, or I like to call them different flavors of DGGS that are derived from the inherent qualities of that DGGS. These are all covered by the standard. So each of these examples on the screen here are compliant DGGS examples. Okay, if you advance one more. Now the beauty, like I said before, you can refine these cells from near global down to sort of micron level, and this gives you, and this is based on a fixed and consistent topology, which threads through a simplicity and a consistency through your range of resolutions. Unlike in the conventional sense, where choices of grid cells and refinement of that are typically arbitrary in nature, although there may be some guidance there. There's no fixed cell size or fixed sort of hierarchy step. With DGGS there is, and that again enables the operation of the sort of the efficient operations of these sort of child and parent sort of hierarchical navigation, because there is a known quantity, regardless of whether we're dealing with the DGGS that's got square cells or triangular cells or hexagonal cells. If you advance one further, yep, and because as Robert said, we're able to provide these a zonal identifier to each of these DGGS cells or zones. This allows us, and with the aid of constructs like space filling curves, it allows us to convert complex multi-dimensional spatial analyses to a set of one-dimensional array processes, which is inherently machine friendly, and a computer can crunch through that a hell of a lot easier than a multi-dimensional array. So if we go one forward, and what this allows us to do, because we're dealing with equal-sized units, being the individual zones, and they all have the same topology, they have the same sort of area and size. What this means is that we lend ourselves to massively parallel operations on individual cells or groups of cells, and this makes DGGS infrastructures massively scalable, from small infrastructures to large infrastructures, from small sort of use cases to large use cases. So if you advance again, Robert. So where does this meet when we look at statistical sort of realms? And in preparing for this seminar, both sort of Rob and I, we took a look at the last coffee talk webinars, which presented some really interesting advancements in the way statistical units are being done in Africa and in Portugal, to improve the sort of the nature of it. And so what I've sort of did is, okay, well, let's take a look at these and just see where does DGGS fit into this? Does it have a role? Could it enhance these I guess use case scenarios or these applications even further? So if we go to the next slide, so looking at the so defining sensors enumerated areas. So one of the problems that deriving your base geometry from dynamic and contextual data is that you end up with complex geometries as your base unit. And this is problematic for a couple of reasons. One, it creates provenance challenges across census data sets. And so, this sort of slide from the previous presentation is highlighting the difficulty from going from an old census of 1991 to the newer, more modern census acquired with a different sort of basis and different geometries, as you can see highlighted in that red circle there. And these features, they may have the same identifier, but they're vastly different in shape. And of course, when we're dealing with coordinate systems, coordinate pairs, and the conventional description of polygons, we have inherent precision errors. If you, depending on how many decimal points you define your polygons to, whether you're adhering to data realistic data uncertainty, you get slithers and you get some sort of errors and overlaps and gaps in your data sets, no matter how much work and effort you put into making them pristine and perfect. There is always going to be this sort of rounding error because of the nature of the data that you're just defining your position as. And of course, the aggregation of enumerated areas, because we're dealing with complex geometries, is a non-trivial task. Yeah, it's possible, and it's been done for quite some time, but it is a difficult task, and so the spatial queries on those complex enumerated areas is also non-trivial, because you've got to then do these complex spatial analytical tests to determine whether you're touching, overlapping inside a particular statistical unit. So if we go forward, so let's take a look at how this might look from a DGGS perspective. So I've just sort of zoomed in on these two examples here. So the bottom one there is the 2001 census, and the top one there is 1991. And the highlighted feature there. Now, sort of caveat: I don't know this data, but let's assume that the highlighted feature is the same identified feature that has changed its shape from one census to another. Demographics have changed, and the boundary has been redone. So there's a few assumptions in this example here. But if we take a DGGS and we apply the DGGS over that, so we have instantly a very simple set of geometries. Now, at this scale, so in this sort of mocked up scenario, we're at resolution 9, and so you can see that both of these areas have the same DGGS zonal identifier at that resolution. So if we step through again, but by the nature of DGGS, we have that the scalable and sort of hierarchies, which allows us to zoom down and get a finer resolution and a better fit for the data as we go down. And you can see there the corresponding identifiers, lists of identifiers. And one thing you can see there with the highlighted numbers is to determine, well, which what's the footprint of these two different areas that are the same. Over on the right hand side, it's a very trivial operation because it's really a list comparison. I've got a list of identifiers for one census, and I've got another list of identifiers. Which ones match? And so if we go down to the next level of precision, we can do that at multiple levels, from coarse sampling right down to really fine sampling, where I guess if you think about it, pixelation sort of artifacts are minimized or even below the inherent data noise threshold. But again, when we're doing even at these fine resolutions, where we're dealing with sets or lists of many DGGS zones, the comparison again is very simple. It is literally a comparison of two arrays of identifiers, which for a computer is very fast operation to do a comparison. We don't need to do constant spatial analytical processes in order to determine whether this feature is the same feature. And that's one of the beauties of DGGS. It provides a simple, globally consistent and hierarchical and fixed set of geometries that can support the data comparisons within and across statistical data sets. Move forward. And then just looking at the other example that was, or the other presentation that was done earlier, they took a different approach with the Grid 3 project, which is more of the grid is not necessarily a data structure, but it's more of a holistic approach. That's actually an acronym. But if you look at their solution, what you see on the screen here, you've got a set of different data inputs. You've got a splitting process, sort of doing some analytics on that, and then you've got some amalgamation and merging at the end to produce value-added interpretive sort of data sets. But there's one clear issue here that is there with all conventional approaches to spatial. And you can see that red line there. There is a divide. So on the top there we have the vector sort of world. So we've got all these different vector layers. We're doing vector analysis on those, and then on the bottom we have rasters, and we can do sort of standard raster stuff, but never the twain shall meet, because in order to do a comparison of rasters and vectors inherently, you've got, in a conventional sense, you've got to rasterize your vector or vectorize your raster, so that you've brought your data into a common baseline in order to do a one-for-one comparison. And this throws up issues around data continuity, data sort of increased uncertainty and errors in the data, any corruption in the data. So there's a whole bunch of issues that raises if you're trying to merge those. And DGGS, by their nature, they enable us to bridge this divide. We have a common geometry. We also have common APIs that unify and sort of unify that analysis across this divide. And as well, with the DGGS, you don't have to resample or process your data in order to combine it. You can literally tag or map your data and create either lookup lists or additional sort of columns of data that represent the DGGS view of that data. And that allows you to leave your data as it is, leave your vector data in its vector context, leave your raster data in its vector context, but also do comparisons, direct comparisons between the two through the aid of a DGGS. Go to the next slide. Okay, so yeah, so that last one was just sort of emphasizing that. So we feel DGGS is the unifying key. It's the infrastructure that allows us to bring all of these different data together, and that's sort of where DGGS shine. They shine when you're integrating data and multiple sources of data, and especially multiple types of data together. As you can see there on this sort of what should be a very familiar diagram to you all. Sort of DGGS is kind of in that middle, in the middle of that diagram, where it's able to bring all of those different data, contextual, societal data, economic data, environmental and physical and geospatial data can be all brought together utilizing a DGGS. If your data set has a description of location or involves location, it is possible to map that to a DGGS and then utilize the DGGS to do spatial and temporal queries of those. And yeah, so if you move forward, and so yeah, so why do DGGS, and we've covered this a couple of earlier as well, but just to emphasize, why does DGGS sort of form that key? And they're inherently multi-resolutional. Our data is multi-resolutional, especially when we're dealing with multiple sources of data. A DGGS inherently is that. It uses simple and fixed geometries, so we don't have that added complexity, even if we're doing conventional spatial analytical processes. We're doing them on simple geometries, not complex geometries. We have global coverage with the DGGS, so it doesn't matter where you are in the world. You have a consistent way of mapping your data that doesn't require you to change your infrastructure if you're taking a statistical analysis from Portugal and then applying it to Canada, for example. We have unique spatial identifiers, which then aids the efficient machine sort of ready or machine friendly use of combining data. And they can be federated multi-organizational spatial data infrastructure across jurisdictions, across organizations, even across the world. They sort of they're ready they're ready for that. If we move to the next slide. So bringing this together, with DGGS, we have search and query operations that are simplified. So we're able to leverage array set theory and database lookup methodologies as opposed to spatial computation. We have a harmonized data model, and so the vector raster divide is bridged, is no longer an issue for us. We sidestep that issue quite effectively. DGGS are scalable. So you can aggregate statistics achieved via summations and various weighted averaging across simple equal area cells or zones. And by that nature and that hierarchical nature and the fixed sort of structure, it is possible to put in place access privileges and privacy constraints around the access to these infrastructures, or the implementations, I should say. And so an example of this is where a member of the general public may be able to interact with a statistical DGGS infrastructure down to a certain level. All right, let's call it, they can go down to, let's say, level 5. All right, which might be a broad area, preserves the data, it doesn't and keeps it suitably disassociated with individual persons or people's private dwellings and etc. While a data curator or administrator, they can go right down to the level of precision that's in the data, and you're able to do that without having to make any changes to your data, without having to create any special public-only data set versus internal. You're able to do that all in the one infrastructure, and I think that's very powerful. If we go to the next one. Okay, and like I said before, DGGS, they can work seamlessly across jurisdictions. And so being a global and a common spatial data infrastructure, the infrastructure and its operation is not dependent on agreement between individual data custodians. And so if we've got, say, two countries in Africa who have just defined different sets of mesh blocks and different sets of statistical grids to meet their own needs, you can have these issues across the boundaries where those two systems don't meet up. Utilizing a DGGS allows each of those countries to define their statistical infrastructures in their own way, but to be able to link those and utilize those statistics across those boundaries through the aid of a DGGS, and that's a very powerful thing that is one of the value propositions of a DGGS. And go to the next one. And so the DGGS indexing of data enables consistent provenance of features to be recorded and tracked over time. As I demonstrated earlier in that sort of mocked up example, you can track how individual features have changed over time, just sort of as a byproduct of mapping or encoding, or not encoding, but mapping that data to the DGGS infrastructure. Go to the next. Yep. And as you saw earlier, like there are different flavors of DGGS, and they will have different internal sort of software implementations on how they're queried. Yes, internally under the standard, they're all implementing the same topologies, but the way they're doing it, and because of sort of the differences in the sort of the cell structures and things like that, the way they do that internally will be different from DGGS implementation to DGGS implementation. Now, ordinarily, this would raise a red flag of, oh well, we've got all this, we've got simple infrastructures, but then we've got this complexity of where different organizations around the world may have different preferences for a different style of DGGS, and then you've got this difficulty of, well, how do we interact and share, transfer, and query data across those infrastructures? And this is where the OGC APIs are really changing this sort of difficulty. The OGC APIs are looking to standardize spatial data across the web, sort of as a general statement. But what we're also doing is we're looking at the drafting, the crafting of specific APIs for DGGS, including a consistent and common query language, sort of languages, and the application of those APIs targeting specifically DGGS infrastructures, but enabling us to throw that data back to an interchange between conventional spatial data and DGGS enabled spatial data without any structural differences. And that's what we're currently doing, sort of to build that consistent layer for the developer and the end user, so that they can just think about utilizing the topologies rather than the individual or driving the individual implementations. Go to the next one. Yeah, and so sort of where are we at to now? What are we planning on doing over the next thing? So a lot of the work that has been recently done, there's been work in terms of the APIs over the last 3 to 4 years. There's been a flurry of activity in the last 12 months through the OGC testbed 16 and the GeoConnections program funded by NRCan. So there's a bunch of things that have come out of those projects that we're now working on through the standards working group. And the first one is to develop a mature DGGS-reference library of implementations, sort of managed through the OGC. We want to explore and elaborate sort of the common OGC APIs for DGGS. We're exploring the opportunities and limitations of DGGS-driven analytics and to elaborate a specific sort of APIs for DGGS. And we want to set up registries of DGGS implementations and live DGGS-enabled data services. As these sort of start to come online, it will lower the threshold and the barrier for adoption and implementation of DGGS infrastructures to use cases such as in the statistics world. And I think that's it. I think the next one's. So any questions?
Yes, if I could just sort of close that off. So the engineering report, which is the sort of major summary of the work that was done for DGGS in testbed 16, is online, and the link is down the bottom there. So that has been published, even though the standard that it was operating on hasn't quite got to full publication yet. So yeah, many thanks. I see we do have a couple of questions in the chat.
Yes, we have 3 questions that are in the chat, and they're all in a way on a similar theme. I think people are really impressed with what you've presented, and they would like to start playing with this. And they're asking generally about tools that can be used. So hopefully you can see now where I've just copied these onto the main screen so that everybody can see them more clearly. Would you like to say a few words on these points?
Okay, so I think actually, so can people continue to see our presentation as well? Because I think actually one of our extra slides addresses one of those things maybe.
Okay, I'll stop sharing and you can put the presentation up. Okay.
So do I need to, yes, I need to turn my sharing back on again, I see.
Yeah.
Yeah.
In order to do that. Where am I? Share and that one. Cool. Okay, so this was the progress we made last year with implementation within OGC API, and we demonstrated both OGC API processes and OGC API features. And one of the cool things that I felt with those is that basically it was utterly standard OGC API notation that was used, but the quirk for it was that if you said you wanted your result of this as a GeoJSON, then you got traditional geometry JSON, then you got zone IDs, and so you were essentially getting DGGS native answers by requesting the answer operate within a JSON environment rather than a GeoJSON environment. Now, the other cool thing that we did, and this gets to, so this is an example of it, of the API being defined in Swagger Hub, and I won't go through the details of that at this point. But then what we did was within GeoServer, a wrapper was made that presents a DGGS as a virtual set of layers, as a virtual set of vector layers. And we did that for two, both a hexagonal and a rectangular or cubic DGGS, the same wrapper. And then just to really ram home a point about the integration, what we did, GeoServer is usually a vector system, but we imported Sentinel data into it and stored that Sentinel data in a backend DGGS data store, which ClickHouse was used, which was a NoSQL database. And so that wrapper and the libraries that were used are all open source. And so I believe that's in the GeoServer repositories now, so that can be picked up. And this had two beauties. One, it allows you to use GeoServer to create a DGGS version of any existing type of data, and we proved it for both raster and for vector. And then that data store can be used purely as a DGGS data store with DGGS analytics on it, or you can use it through GeoServer and then be able to achieve, you know, all of your WMS and WFS representations of that data just by continuing to use GeoServer. And so that was quite a powerful demonstrator, and we proved how efficient, if you like, that you could use within DGGS, that you could do Earth observation raster processing in a vector in what you would initially have thought was a vector engine. And so this is a quick summary of some of the libraries that are out there at the moment, the ones we examined. And the top two, H3, which has been created by Uber, and our HealPix, as I suggested, is my own one, were the two libraries that were wrapped for this. So I think that answers the first question, and maybe it leads to the others. I can't now see the question. There should be a chat somewhere. Do you want to re-share your screen now?
Yeah, I'll put the questions up again, and we've had a couple more come in as well at the same time. So I think the last one is also tools based from Anna. So hopefully you see those now. Okay, so yes, so that demonstrates the vector representation, and well, in fact, in that display of ones, you saw some of those are Python, some of them are C with Python bindings and the like. There's ones in there that are actually in R.
So yes, we've got both R and Python available there. Do we need special arrangements, converting existing data, storing and presenting web maps? If so, do you provide tools? Okay, well, as I mentioned, basically any database can be used that can process large lists. And ClickHouse happened to be the one that was chosen for our testbed work last year, and that was certainly a really powerful technique to use. And you can have ClickHouse on the desktop as well as ClickHouse in a multi-threaded server environment. And I think what we'll start to see is we're working with the Geospatial standards working group at the moment, and so the language that we've been working with is now being shared with the Geospatial implementers, commercial implementers and open source implementers. So I think we'll start to see all of those start to emerge over the next while. And as I said, GeoServer is there, which means that you can access it through QGIS, of course, as an example. Next question on Mohammed, I think I see you're asking your thoughts on using DGGS in routing. Look, absolutely. In fact, I'm working with a standards group in New Zealand, which is coming out of the New Zealand Transport Authority. And of course, routing is one of the things that they are interested in. And if you think back to the data type that I noted, you remember there was a column of lists, and then a column, of each list, there was a directed list, was its alternative. And so a directed graph is essentially a navigation or routing type application, and directed graph would be the data type that you would use on that. So basically, we are exposing DGGS through there to any graph database, and if you've got a graph database, then you can start to do your routing algorithms on that graph database.
So one thing,
I see that Anna.
Yep.
If I could start just by quickly apologising that I was aware that maybe we should have emailed both of you to alert you, maybe even get permission to do that. So Anna, thank you for being accepting of that.
Yep. I guess just touching on the routing, well, both the routing and the sort of the raster and that. So in testbed 16, there was examples of utilizing DGGS with both raster coverage data and vector data. Some of the work I've been doing with NRCan has exposed a very simple way, and it's almost trivially simple from a DG's perspective, to engineer routing issues, a routing scenario where with the DGGS, you're essentially mapping along those sort of linear features, and then it's literally a sort of follow the index breadcrumb as you sort of move down that route, as opposed to having to go, oh well, I've flipped from this linear feature to that linear feature. Are they connected? Are they not? Do we need to make a hop? All of these things that plaguing sort of the routing space become a much less, if not a non-trivial, a trivial sort of issue. So it's it's encouraging to see sort of as we start doing more work on not so much the structures of DGGS, but actually the applications of DGGS, how flexible they are and how well suited to new opportunities with our data. So it's quite an exciting space to be in.
If I could address the processing speed issue, which I think a couple of people are starting to ask about. No, we haven't explicitly done tests on that in anger yet. I think one of the interesting things, one of the things I found interesting, a lot of work has been done on working around the performance issues inherent in the computational complexity of GIS. Obviously, that sort of tuning has yet to happen in the DGGS space. But despite that, we are seeing pretty favorable comparisons when you start to see things. And I think what we're starting to see, I think the thing that's really coming through is that, there was a phrase that we always used to use within Landcare Research, and I've heard it elsewhere too. The difference between the thinking time for constructing a problem and then the GIS time to actually achieve the result. And a lot of that GIS time is not the processing time per se of the final analysis, but the preparatory time of getting everything ready for analysis and the diverse ways that you have to do that. And what we're seeing here is that DGGS essentially cuts through that, because you're setting up a circumstance whereby you can bring data to it once and then use it for a great variety of different applications afterwards, rather than having to bring your data together separately for each application, which is traditionally the way that it is often done. And that simplicity, it's difficult. I really can't overstate that simplicity and the benefits of that.
Yeah, and I guess to add to that, there is a marked difference between a DGGS engine or a DGGS library and an optimized production-ready DGGS implementation. And so, like a lot of the, efficiency issues that you sort of hit up against when you're implementing a DGGS are standard ICT infrastructure-related problems, not problems that are inherently related to a DGGS. But that said, if you took just a generic, sort of one of the generic open source DGGS libraries off the shelf, and then just applied it without sort of careful consideration about how you were implementing that in a system or an implementation or infrastructure sort of stack, then you may sort of see some issues. There are some really good examples of well-constructed DGGS implementation. One being the sort of the Pixis or Global Grid Systems implementation, which is a very fast operating DGGS that can do DGGS mapping on the fly, and a lot of that is due to the effort that's been put into building out the functionality or the of that DGGS infrastructure at the core. So it's there's a lot of general sort of infrastructure issues that are separate to a DGGS that you need to be mindful of. And I guess in some regards that does touch on the question about Sentinel versus Landsat data. So So my background in history was I was one of the troublemakers who started the Australian Geoscience Data Cube, and which then spawned the Open Data Cube. And one of the problems that taking that conventional approach to tiling sort of individual data up at an arbitrary scale was that you can tune it to Sentinel data or you can tune it to Landsat data, but having those work between the two doesn't work. DGGS infrastructure is different because you're not tailoring it to any one particular data set or data format. You're like the DGGS infrastructure or the structure is separate to that, and that allows you to map Sentinel data and Landsat data and any other sort of data or airborne photography, geophysical data, contextual data, able to map that sort of consistently without having to change the nature of your whole infrastructure in order to do that. And that's a really powerful powerful thing that a DGGS infrastructure provides. It's which the sort of the data cube sort of community are hitting up against these problems because the infrastructures are too tightly coupled to their data sources. A DGGS is decoupled from any data source.
So that's great. I think what we're seeing is that DGGS is providing a really powerful, really flexible approach to dealing with many of these practical issues. We are a few minutes over. We started a couple of minutes late, so it's not quite so bad. But I just want to check if there are any final questions or comments.
Anna, I'm happy to follow up with you. And in fact, I see that Stephen has put in the link, or maybe, no, it was Ryan, has put in the link to the engineering report in the chat. And those slides, those extra slides that I provided at the end there, that's all taken from the report. So that report has got the how we did the Sentinel analysis and how we did the OGC API features and processes in much more detail. If you want to go have a look at that. And Matt or I, or any of the others involved in that, you'll find reference to in the report. I'm sure we'd be more than happy to answer questions if people want to follow up on any of those things.
Great. I don't see any further questions. So I think it's been a very comprehensive presentation and discussion, lots of information, and I'm sure lots of inspiration as well, lots of ideas. That's the sense I get coming out of what's been posted in the chat. So I'd like to now thank our two speakers, Robert and Matt, for giving the excellent presentations and getting this discussion going. I'd like to just mention that the presentation and the recording will be posted on the website for the coffee talks. So they'll be available probably tomorrow. I should get a chance to put those up. And just to finish, I'd like to just mention again that this is one in a series of coffee talks on a range of different topics relating to bringing together geospatial and statistical information. And I'd like to make an offer to all of the people connected. If there are any particular topics you would like to hear about, please let me know. stephen.vale@un.org, but you have that address anyway from the invitations. And also, I'd be particularly interested if anybody would like to volunteer to present some of their work or something that you think would be useful for the wider community. So I think on that point, we'll end for today. Thank you, everybody, for joining the meeting, for the excellent questions, and thank you again to the two presenters. So have a very good rest of the day, whether it's breakfast time or dinner time, whatever it is for you. Please enjoy the rest of the day and hopefully see you next time. Thank you.
Many thanks, everybody.
Thank you. Take care, everyone.